Hi everybody. Today I'd like to go over a problem that gives kids headaches once in a while. And this is dealing with what's known as an Atwood's machine containing a massive pulley. Okay, Atwood machine with a massive pulley. Here's the setup. We have this 0.2 kilogram disc here. And it's acting as a pulley, and we have lightweight string draped across it with a 0.8 kilogram mass over on the left and a 0.4 kilogram mass over on the right. There's also some friction here at the axle of the bearing, and it produces a constant torque of 0.35 Newton meters right here at this, so a retarding torque of that much, so we need to consider that too. Now let's say that I'm holding this 0.2 kilogram mass, and then I suddenly let go, I release it. Okay, what's the acceleration of the hanging masses when they are released? What are the tensions, T2 and T1? And then what's the upward force that the pulley bracket exerts when during this acceleration phase? Okay, so those are the three questions we're going to try to solve. Before we get into that, though, let's think conceptually as to how big some of these forces are. Okay, so let's take a conceptual approach first, and let's take a look at this right here. This is a 0.8 kilogram mass. Okay, so what would the and we're just doing it conceptually. Okay, so the weight would be mg. All right, so that would so is mg over here bigger than or equal to T2? Is T2 bigger than, less than, or equal to T1? So let's say we'll call this mg2 over here, m2g I should say, and this might be m1g. So considering m2g and considering T2 and considering T1 and considering m1g, how could we relate them together in terms of inequalities? Is this greater than this, or equal to this, or less than? What do you think? What do you think we have here? Well, because this pulley is so massive, okay, it has a lot of rotational inertia. And so therefore, when this weight is released and tugs, okay, the tension here, since the overall movement is downward, the tension too must be smaller than the m2g, or the weight of this 0.8 kilogram mass. So I'm going to put m2g is greater than T2. What about getting back to the rotational inertia of this disk? If we compare T2 with T1, T2 is going to pull quickly, but because the disk has so much rotational inertia, it's going to resist being rotated, and so therefore the other side won't feel it as much, and so T1 will be less than T2. So T2 is greater than T1. Okay, now the overall movement is like this, right? Okay, so it's going to go down. The m2g is going to go down, and I mean the 0.8 kilogram mass will go down, and the 0.4 kilogram mass would go up. And so therefore T1 must be bigger than m1g. So conceptually, the weight of this 0.8 kilogram mass, m2g, is going to be bigger than T2, And because of this inertia of this disk, T2 will be greater than on the other side of the disk, T1, the tension in that side of the string. Okay, since 0.4 kilogram mass is moving upward, that must mean that T1 is bigger than M1G. Okay, so this is a very important concept to understand before we even get into the numbers. Okay. Alrighty, so let's get started. This massive pulley has a lot of rotational inertia, and so therefore, what we need to think about is torque and moment of inertia. Okay, so let's think about that. Okay, we know that the sum of the forces equals ma, and so the analogy of that would be that the net torque, or sum of the torques, would be equal to I alpha, just like sum of the forces is equal to ma. All right, so we can start with that, and we have some torques exerted by these forces here. Let's figure out what the forces are first of all. Well, actually, we can just, these forces are not as relevant here, M2G and M1G. That's kind of a newcomer's mistake. What really is important are these tensions here, T2 and T1. So let me draw another little view down here. Okay, so here's the disk, and here's the bracket, and here's T1, and here's T2. So this is an important way of thinking about it. Now we know the radius is 0.15 meters for each side here. So this is the moment arm, right? At 90 degrees. So the torque would be T1 times the moment arm, 0.15, and the torque on this side would also be T2 times 0.15, since the radius is the same on each side. Okay, so I can go ahead and substitute in. We have 0.15 for the moment arm times T2, so that's moment arms times force gives me a torque that would cause counterclockwise rotation. Okay, minus the torque that would produce clockwise rotation, which would be 0.15 again times T1. Remember, we also have, if we look back up here, there's bearing friction, which is producing a retarding torque, and that's 0.35 Newton meters. That's constant. So that's going to retard the system too. So I'm going to put 0.35 in for the torque due to the friction in the bearings of that axle. Okay, that all is equal to I alpha. Okay, but what is I? I is the moment of inertia of the disk. And the moment of inertia of a disk is 1/2 times m r squared if it's pivoted around the center of mass of the disk. Okay, so that's I right there. Okay, so we have that, and we can see that this is 1/2, and the mass is 0.2 kilograms, and the radius is 0.15, and that is squared. Okay, so this is what we want to put in for the moment of inertia. Excuse me, there's the lights went off again. The moment of inertia for that disk, and I can substitute that right in here for I, right here. Okay, so now we can simplify it a little bit and so forth. Okay, we also know what alpha is. According to our unit circle, We know that S equals R theta. We know that if we divide both sides by T, we get V equals R omega. And we get, if we divide both sides by T again, we get the linear acceleration equals R alpha, the angular acceleration. So therefore, if we rearrange that, we get alpha equals A over R. So this is an important thing that we can substitute in for alpha right here. Okay? So if we just go ahead and substitute some of these things in here, we can take these two. Let's see here. I'm running out of space, but that would be 1/2 times, well, I can maybe just 1/2 times 0.2 would be 0.1. I'll just simplify that there a little bit. So this is 0.1 times 0.15 squared times A over R, and R is 0.15. So I'm leaving that all in there because I can see that a lot of our 0.15s will cancel out. Okay. So what do we have? We have, if we divide both sides by 0.15, we don't have it here. Well, I can divide that by 0.15 also. Well, at least the one thing we can do, I don't want to do that right now. One thing I can do is just, here's a 0.15 in the denominator, here's 1 in the numerator. I can just cancel that out. Okay, well, hopefully you didn't get too confused, but so we end up with, I'll just rewrite it again, 0.15 T2 minus 0.15 T1 minus 0.35 equals, and then 0.1 times 0.15 is 0.015 A. So this right here is a result that we can keep. Okay, so far so good, but we have 1, 2, 3 unknowns. So we're going to need to have a couple more equations in order to solve for those 3 unknowns. Okay? So far so good? Okay. Now let's move on to the next step. I'll just write that result up at the top here. So far we have 0.15 T2 minus 0.15 T1 minus 0.35 equals 0.015 A. So there's our first equation that we can keep. Alrighty. Now, if we think back to our pulley system, we have this tension here. We have the tension pulling down here. That's T2, and we have a tension pulling down here. That's T1. But those tensions are produced by the hanging weights that are falling. So we need to think about the weight aspect there. This would be M1G, the weight there, and this would be M2G. Now M2G, what would that be? That's 0.8 kilograms times 9.8, which gives us 7.84 newtons of force. And this one here, M1G, would be 0.4 kilograms of mass times 9.8, which would give us 3.92 newtons of force. Okay, so now let's draw a point object. Let's make this mass right here on the left be our point object, and we have our M2G pointing downward and our T2 pointing upward. I'm going to draw it bigger below here and just draw it sideways. Okay, so we have This right here would be M2G, which is 7.84 newtons. And pulling the opposite direction would be T2, smaller. I'll just call that T2. Okay, now let's take a look at the other mass. The other mass that's hanging from the string. The T2 is bigger. T1 is bigger than this. So I'm going to make T1 a little bigger. So we'll call that T1. And then pulling the other way, it's a little smaller. That would be 3.92. Okay, now I'm going to let to the left be positive in this case and to the right be negative, so I'm going to make that a negative right there. Alright, so if we think about our Newton's second law, the sum of the forces equals ma, we can apply that to both of these situations here. This would be m2a. Alright, so let's take a look at this point object right here. We'll say 7.84 plus a negative or minus T2 equals M2, which is 0.8 kilograms, times A. Alright? And that's a good equation. That's a nice keeper right there. So I'll call that equation 2. Now let's do a similar thing for this point object. So we have T1 plus a negative or minus 3.92 newtons is equal to M1, which is 0.4 kilograms, times the same acceleration. These are both accelerating at the same rate. Okay, so here's our third equation. I'll just label that number 3. So that also is a keeper, as we would say. Alright, now if we substitute 3 into 1, so here's 1 up here, remember, we got that from the sum of the torque equals I alpha. If we substitute equation 3 into 1, that would be, we can then figure out, we can then consolidate. Okay, so let's substitute that in up there. And so just solving for T1 here, T1, let me just write that here, T1 is equal to 0.4a plus 3.92. Now I can sub that up here and substitute right in for T1 of that equation. And so we can get 0.15 T2 minus 0.15 times T1, but T1 is equal to this, so it would be times 0.4a plus 3.92, that's T1 right there, minus 0.35, which is that torque due to the bearing friction, equals 0.015a. Okay? Alright. And then just expanding this out a little bit, I won't even talk. Okay, and now simplifying. Alright, so by taking equation 3, substituting that result from a 3 into T1 in equation 1, we get this. I'll just call that equation 4. Okay, so that was my method. Of course, in algebra there are many ways to do these things. Okay, now if we try substituting equation 2 into equation 4, that would be, an option. Okay, so let me just change this over and solve for T2 first. T2 would be equal to 7.84, okay, minus 0.8a. Okay, so I can take that now and substitute T2 in up here, and now we can see what we get. All right, so I get 0.15 times T2, but T2 is 7.84 minus 0.8a, and then minus 0.938 equals 0.075a. Let me move that over. So 0.075a. All right, and we can go ahead then and simplify it. So I just won't talk on it at this point. Okay. And continuing to simplify. And we get our acceleration. Okay. Ta-da, we got one. Okay, so we had to use 3 equations to solve for those 3 unknowns. So that meant that we had to deal with the sum of the torques equals I alpha, and the sum of the forces equals MA. Those were our 3 equations. Okay, now if we think back to our original problem, we got the acceleration taken care of the hanging masses. And since there's no slippage in the string, that also means that that's a linear acceleration along the curve. That's why we could use this relationship here, because there was no slippage, no slipping along the rim of the disk. All right. Now, we also have a couple other things we need to find out. We need to find what T2 and T1 are. And then once we find those, and that's while the acceleration is happening, and then we need to find out what the upward force of the bracket is on that pulley while the masses are accelerating. Okay, so let's solve for T1 and T2. We already have the setup for them. All we have to do is plug in the acceleration that we just found. So we can plug in the acceleration right here, and the same one right there, and we can solve for it. Okay, so just moving down here, T1 is equal to 0.4 times A, which is 1.22 meter per second squared plus 3.92. And when we do that, we get that T1 is equal to 4.41 newtons. Now we can repeat the process for T2 using it right here. using that relationship, T2 is equal to 7.84 minus 0.8 times A. And remember, A is 1.22 meters per second squared. When you do the math, you get something. What is it? Okay, 6.86 newtons. Okay, so now we have what T1 is and what T2 is. Very good. Our last step, we need to find the upward force the pulley bracket exerts on the pulley during the time when the weights are moving, accelerating. Okay, well, to do that, I probably should get another page and let's think a little bit of what the system we're dealing with is at this point. We're talking about that bracket there exerting an upward force on this big pulley disc. Okay, so I'm going to draw, so I'm going to use the center of mass of the system here as a point object. It's probably a little bit below the center of mass, is probably a little bit below the pivot point of the pulley, but so this is the upward force of the bracket on that pulley. I'll just draw it in red. Okay, now we also have the downward forces, okay, acting on that pulley. We have T2, okay, which we found out was 6.86 newtons. And we also have T1, which we found out was 4.41 newtons. Okay. We also have the weight of the disc itself. Now the weight of the disc, or the pulley, it was a 0.2 kilogram mass, right? So that would be 0.2 kilograms. That'd be mass of the disc times G. So that'd be 0.2 kilograms times 9.8 meters per second squared. And that gives us 1.96 newtons for the weight of the disc. Okay, so we have 3 downward forces acting on the pulley, and we have the bracket's upward force acting on the pulley. And this whole system, the center of mass is not changing for that system here. So therefore, the center of mass is our point object in this case. I can redraw it. There's the center of mass. We have the upward force there due to the bracket. That's equal to the 3 downward forces due to the tensions and due to the weight of the disc. So in this case, since this whole system here, the center of mass is not changing, we can say that the sum of the forces, or the net force, is equal to 0. In other words, the ups have to equal the downs. Okay? So that's not such a bad thing. Okay, so we can say that then the up, which is what we're looking for, F upward of the bracket, is equal to the downs, which would be what? 6.86 newtons plus 1.96 newtons plus 4.41 newtons. And when you add that up, the upward force would equal 13.23 newtons. Okay? Now, if you compare that with the static situation, this is the upward force of the bracket as those weights are accelerating. How about if the weights were just hanging there? What would the upward force be? Would it be more or less? Well, it turns out that the upward force of the bracket, if the weights were just statically hanging there and not accelerating, would be more. Okay? If we add up the three weights, okay, if we add up the three weights, we would get 13.72 newtons, which would be more than the upward force of the bracket while the system is accelerating. So that's kind of interesting, huh? During the acceleration process, this bracket here doesn't have to exert as much upward force compared to if the weights are just hanging statically on it. Okay, thanks everybody. We're done with this problem.